A new AI model, despite its small size, now performs like the most massive systems available. This breakthrough fundamentally changes how we can develop powerful and efficient AI. Let's get into it. Let's start with today's featured paper, Scaling the Horizon, Not the Parameters, Reaching Trillion Parameter Performance with a 35B Agent, by Agents, a team from Shanghai Artificial Intelligence Laboratory. This paper presents a landmark result demonstrating that a much smaller model can achieve the performance of a trillion-parameter model by scaling its reasoning horizon, fundamentally altering the calculus of model size versus agentic capability. Here's a full breakdown.
To start, we build a foundational understanding by processing a vast training corpus containing everything from web data and books to code. From this, we extract and structure agent behaviors into a knowledge action graph, or KAG, which maps out correct and incorrect action sequences. Feeding into this, we then develop specialized teacher models for different areas by choosing a specific domain like coding or scientific research. This creates expert subgraphs, such as the scientific KAG, which capture deep knowledge for those particular tasks. Next, we use an innovative technique called self-play graph search and expansion to distill the knowledge from these multiple teachers back into our main agent. This process explores different action paths, guided by the specialized knowledge, to continuously expand and refine the central knowledge action graph. The agents, one method consistently outperforms other models, including GPT 5.5 High, on several benchmarks such as Frontier Science Olympiad, SEAL, Zero, and IFEVAL. It achieves the highest scores in many categories and is highly competitive across all 12 benchmarks shown.
Up next, our second paper out of 10, CAREBench, a child safety risk benchmark for language models by Kavya Krishnakumar and Jonas Mueller from Handshake AI. CAREBench introduces a crucial and timely benchmark for evaluating nuanced, pre-escalation child safety risks in AI, moving beyond existing metrics to address subtle harms like manipulation and emotional dependency. Let's break down its key contributions.
Let's start on the left with the prompts section, which represent user inputs that might contain risky requests. These are fed into a language model, which then produces the generated responses you see in the middle. Feeding into this process, the prompts themselves cover a range of risks, representing different categories of potential harm. For instance, you can see specific examples like a request for a pet scamming script or blackmail dialogue. Next, a crucial part of this benchmark comes from the parent/clinician annotations panel in the lower middle. These experts provide labels like acceptable or unacceptable to ground the evaluation in real-world safety expertise. Finally, these expert annotations help calibrate the multi-judge evaluator on the right. This system then applies the evaluation criteria to make a final decision on whether a model's response is acceptable or not. The Claude models, particularly Claude Fable 5 and Claude Opus 4.6, demonstrate substantially lower overall failure rates, with Claude Fable 5 achieving just 2.3%. In contrast, GPT 5.4 performs significantly worse, showing the highest overall failure rate at 58% and high failure rates across most risk categories, including 85% for online grooming.
Up next, our third paper out of 10, MirrorCode. AI can rebuild entire programs from behavior alone by Tom Adamczewski and Daniel O'Connell from Epic AI. This paper introduces a landmark benchmark that defines a new, significantly harder, and more realistic measure of progress in AI code generation that will likely drive research in the field for years to come. Let's break down its key contributions.
To create a robust benchmark, we first considered potential failure modes, which we categorized into two main groups. These are false negatives, where a correct solution might fail, and false positives, where an incorrect solution might pass. A key challenge is when the details of intended program behavior are unclear. To address this, the AI can send arbitrary inputs to the reference binary to see the expected output, allowing it to learn the functionality through interaction. To ensure solutions are robust, we use held-out tests cheat-proof the benchmark. Ultimately, a solution must produce byte-exact output across many tests, verifying true functional equivalence. We also address cases where language/system built-ins make a problem trivial. To prevent this, target programs are selected to avoid such issues, ensuring a challenging and diverse problem suite. On the MirrorCode tasks, Claude Opus 4.7 achieves the highest average rate of 100% solves. It substantially outperforms GPT 5.5 and Gemini 3.1 Pro preview, which show progressively lower solve rates on this benchmark.
Up next, our fourth paper out of 10, Optimizing Expert-Designed Crystal Graph Networks for Bandgap Prediction with an Autonomous LLM Research Loop by Chinmu Zhang and Boris I. Jakobsen from Rice University. This paper demonstrates a landmark achievement in autonomous AI capability, showing that a general-purpose agent can independently outperform human experts on a standard scientific benchmark, signaling a new era of AI-driven discovery. Let's break down its key contributions.
This table tracks the experiments run by our autonomous agent, starting with the seed baseline in Experiment 1. Each row shows a new change the agent proposed, leading to a progressive drop in the mean absolute error, or MV. Next, in Experiment 25, the agent introduced element pair features in the Edge MLP. This change, which relates to the material's composition, further reduced the ME to 0.1636 electron volts. Feeding into that, the agent later added a space group embedding in Experiment 63. This change, which captures crystal symmetry, brought the error down even more to 0.1578 electron volts. Ours from-scratch GNN achieves a validation MAE of 0.148 electron volts, outperforming all other GNN and composition-based models shown. However, it is slightly outperformed by several foundation models that utilize external pre-training.
Up next, our fifth paper out of 10, Clinical Reasoning Graphs. Structured Evaluation of LLM Diagnostic Reasoning Reveals Competence Without Consistency by Nisarg Patel from University of California, San Francisco. It introduces a powerful new methodology for evaluating the structured reasoning of LLMs in high-stakes medical diagnostics, revealing the critical distinction between correct answers and sound clinical logic. Let's break down its key contributions.
Let's start by looking at this entire diagram, which is an example of a clinical reasoning graph. It visualizes the diagnostic process, showing how different pieces of information are weighed and connected across phases to reach a conclusion. Feeding into this structure is a domain-grounded ontology, which defines specific types of nodes and edges as detailed in the legend. For instance, we have nodes for a clinical feature and edges showing what supports or argues against a diagnosis. Next, the system applies this extraction pipeline to a large set of diagnostic traces, and here we see one example of that process. It begins in Phase 1 initial assessment, where potential diagnoses are assigned confidence scores based on early features. Finally, the paper evaluates reasoning consistency by comparing how graphs like this one change across similar cases. This is captured by the reflection phase, where new information can lead to a promoted diagnosis, as shown by the final arrow leading to the revised conclusion. Overall, the pool performance across all models and conditions shows a very small effect size, with a d-value of 0.04. However, Opus 4.5 and Gemini 3 demonstrate statistically significant small to medium effect sizes in their baseline condition, with d-values of 0.22 and 0.26 respectively, indicating better performance in the W condition.
Up next, our sixth paper out of 10, SWE-INTERACT. Reimagining SWE Benchmarks as User-Driven Long-Horizon Coding Sessions by Mohit Raghavendra and Yoonjung He from Scale AI. This work introduces a new benchmark that fundamentally reimagines evaluation for coding agents by moving from static, one-shot problems to realistic, interactive, and long-horizon sessions, which will shape future research. Let's break down its key contributions.
Let's start with the overall test bed, which is contained within this sandbox environment. It's made up of two key components: the SWE agent container, where the agent works, and the user agent container, which simulates a developer. Feeding into this, the agent operates in a realistic developer workflow, using a shell to read and search the repo. This contrasts with other benchmarks by requiring the agent to explore the codebase itself rather than having everything provided up front. Next, we have the dynamic user simulator, represented here by the user agent container. It provides an initial task goal and a user persona, starting the agent off with intentionally vague instructions. Finally, the system enables an iterative feedback loop where the agent can explicitly ask user for a review of its plan or code. The simulator then inspects the agent's work and provides new feedback, guiding it toward the solution. The multi-turn method, labeled ours, performs worse than the single-turn baseline in terms of resolve rate across all models. For instance, GPT 5.5's resolve rate drops from 48.0% to 24.7% with a multi-turn approach, which also significantly increases steps, tokens, and cost per trial.
Up next, our 7th paper out of 10, SEVA, Self-Evolving Verification Agent with Process Reward for Fact Attribution by Aoji Yuan and Yu Zhao from University of Southern California. This work tackles the critical problem of LLM hallucination with a novel verification agent that provides structured, actionable feedback, representing a major advance towards building auditable and self-correcting AI systems. Let's break down its key contributions.
At the top, we see the core of the system, which takes a claim and a source's input. This information is fed into the SEVA verifier, an agent that analyzes the relationship between the two. The verifier then produces a detailed structured output, breaking down its analysis. This includes everything from evidence alignment and a step-by-step reasoning chain to a final label and an error diagnosis. Next, to improve the verifier, the system uses a special training signal during the refine stage. This is where the novel process reward comes in, helping to fine-tune the model more effectively. Finally, all of this is part of the self-evolution loop shown at the bottom. The agent cycles through verify, reflect, probe, and refine steps to continuously identify its own weaknesses and improve over time. The SEVA GRPO 3B method achieves the highest score on TRQA with 82.7, substantially outperforming other models such as GPT-4o, Mini, and Mini-Check, FT5. While GPT-4o, Mini leads on Fever and Mini-Check, FT5 on Halley, SEVA GRPO 3B shows competitive performance on ClearF.
Up next, our 8th paper out of 10, Arko-T, a foundation model for text-to-structured 3D generation by Liang Wang and Li Tao Chen from Spatial Design Intelligence Lab, BIT-INF Limited. This work addresses the critical and difficult leap from generating unstructured 3D meshes to producing editable, parametric CAD models, a step with enormous real-world significance for engineering and design. Let's break down its key contributions.
On the left, we have typical visual 3D generation, which produces a static, uneditable appearance asset. Our approach, shown on the right as structured 3D generation with Arko-T, instead generates an editable design entity directly from text. A key part of this is how we align the entire process to a formal design state. This means the generated object isn't just a shape, but an editable entity that exposes its underlying parameters and features, like the flange thickness. Next, to ensure the integrity of these features, the model is trained with execution-grounded supervision. This means we verify the generated design by actually running the code. This image displays a code snippet for generating a 3D model of a louvered ventilation plate, along with the resulting 3D rendering. However, the provided content does not include any information about its performance compared to prior work, baselines, or specific metrics.
Up next, our 9th paper out of 10, Experience Graphs, the Data Foundation for Self-Improving Agents by Gang Liao and Daniel J., a body from Meta Platforms, introduces a powerful and necessary conceptual framework, the Experience Graph, that provides the data system's foundation for building truly long-horizon, self-improving agents. Let's break down its key contributions.
First, let's look at the core idea, which is to structure all the agent's experiences into a graph. This experience graph captures everything from tasks and sessions to specific artifacts and prompts, with a fundamental graph structure represented by these nodes within the Trellis Data Foundation. Building on that, we introduced Trellis, our specific data foundation that treats this experience graph as a proper, queryable database. This allows us to use standard database languages like SQL, Cypher, and vector search to interact with the agent's history. Next, we leverage this database structure for powerful access patterns, such as creating these training views. These are materialized views over the agent's operational state, allowing us to easily sample data like SFT trajectories or DPO preference pairs for model training. Finally, this entire system enables a stateless agent architecture, where the inner loop agent session is just a compute unit. This creates a robust, self-improving flywheel, where better data from our experience graph is used to train better models, which then perform better exploration to generate even better data. The computer science methods with p equals 0.1 and p equals 0.5 achieve a 1.2x speedup in best fitness significantly faster than the baseline, no memory, reaching this threshold by approximately step 5 compared to the baseline step 51. While the computer science methods demonstrate substantial early performance gains, all methods converge to similar best fitness speedups by the end of the evaluated steps.
Up next, our 10th paper out of 10, a machine-verified proof of a quantum optimization conjecture by Yuri Cole and Dirk England from Center of Mathematical Sciences and Applications, Harvard University. This is a landmark demonstration of AI-assisted science, using an LLM to solve a decade-old conjecture and then formally verifying the result, with profound implications beyond its specific domain. Let's break down its key contributions.
First, we take the input problem and formalize its components and known parts within the Lean-4 proof assistant. This process reduces the complex conjecture into a single, manageable mathematical statement, our Lean-4 formalization. Driving this entire central process is a large language model, specifically the one labeled LLM, Claude Fable 5. This agentic system is responsible for generating the proof from the initial natural language plan all the way to the formal code. Next, an interactive feedback loop is established where the Lean-4 compiler sends back compiler diagnostics like type errors and open goals. This allows the model to iteratively refine its reasoning and code until the proof is correct. Remarkably, this process enabled the model to uncover a hidden dynamical symmetry within the problem, a genuine mathematical discovery. This novel insight was the key to constructing the final, elegant proof, which isn't explicitly drawn, but is the content of the final output.
Those were today's top papers. Now let's zoom out. ArXiv received 534 new computer science papers across 48 subfields today. Here are the trending areas shaping the field. Looking back at today's research, we see a strong focus on multimodal LLMs and agentic AI pushing boundaries. It's fascinating to also see autonomous LLM optimization loops emerging. Let's dive into each of these key trends.
Trend 1 of 10. Unveiling domain evolution and status. This trend explores the evolution, status, and impact of diverse domains, technologies, and social phenomena. This cluster covers 10 papers. Representative work includes the body as status, muscularity, engagement, and body image risk on #GymTalk, the longevity of innovation, and revealing the technology development of natural language processing, a scientific entity-centric perspective. Trend 2 of 10. Multimodal LLMs for visual tasks. Leveraging multimodal large language models to process and understand visual information for diverse tasks, from data creation to complex reasoning. This cluster covers 64 papers. Representative work includes unlocking the visual record of material science, a large-scale multimodal dataset from scientific literature, how LLMs see creativity, zero-shot scoring of visual creativity with interpretable reasoning, and can MLLMs critique like humans? Evaluating open-ended aesthetic reasoning in multimodal large language models. Trend 3 of 10. Benchmarking AI models and safety. This trend focuses on evaluating, comparing, and improving AI models, often through benchmarking, to ensure performance, robustness, and safety across diverse applications. This cluster covers 67 papers. Representative work includes diversity is the strength of the AI crowd, benchmarking geospatial foundation models for agriculture applications, and CAREBench, a child safety risk benchmark for language models. Trend 4 of 10. Probabilistic learning and data structures. Leveraging probabilistic methods to learn from data, infer hidden structures, and ensure robust, calibrated predictions. This cluster covers 68 papers. Representative work includes adjusted Wasserstein distances for bridging empirical and true distributions with applications to MDS, IBBS, coordinate-free inference of latent submanifolds using random distance matrix theory, and learning as observable matrix dynamics, diffusive relaxations versus phase transitions. Trend 5 of 10. Pose estimation and geometric perception. Focuses on determining object position and orientation, and understanding 3D spatial structures and relationships from various sensory data. This cluster covers 70 papers. Representative work includes Pose Shield, Neural Collision Fields for Human Self-Collision Resolution, MF, UAV Pose 6D, a model-free monocular 6DoF pose estimation framework for fixed-wing UAVs, and accurate recognition of pneumonia and COVID-19 by geometric shape normalization of lung region using automatic landmark detection and piecewise affine warping. Trend 6 of 10. Agentic AI for task automation. This trend explores AI systems that autonomously perceive, decide, and act to automate diverse tasks across various domains. This cluster covers 78 papers. Representative work includes GUI Crafter, weekly supervised UI agent leveraging massive unannotated screenshots, PSBPO, prefix sampling PPO for critic-free RLHF, and Topo Agent, an agentic framework for automated topology learning in medical imaging. Trend 7 of 10, securing and understanding AI systems, focuses on safeguarding AI systems from attacks, understanding their vulnerabilities, and leveraging AI for security applications. This cluster covers 40 papers. Representative work includes MicroAgent, context-augmented multi-agent framework for automatic microservice decomposition, rethinking generative reconstruction attacks against graph neural network models, and uncovering similar but different packages in PyPI and potential security threats. Trend 8 of 10, optimize control for robotic systems. This trend explores advanced optimization techniques to enhance control, performance, and efficiency across diverse robotic and autonomous systems. This cluster covers 43 papers. Representative work includes privacy-preserving decentralized cooperative localization with range-only measurements, a convex optimization-based approach, lateral string stability for vehicle platoons, and evolutionary hyperparameter optimization to find lightweight CNN models for autonomous steering. Trend 9 of 10, autonomous LLM optimization loops. This trend explores using LLMs for autonomous optimization, self-improvement, and iterative refinement of models or systems. This cluster covers 57 papers. Representative work includes toward secure and reliable PDL formalization of large language models with planner-in-the-loop feedback, demystifying the design space and best practices for heterogeneous LLM inference and serving and bash commenter. Leveraging syntax-aware preference optimization to reinforce large language model for bash code comment generation. Trend 10 of 10, proving fundamental math and quantum. This trend rigorously proves fundamental mathematical concepts and quantum phenomena, often using formal verification methods. This cluster covers 37 papers. Representative work includes a machine-verified proof of a quantum optimization conjecture, 3 packings and triangulations, algorithms, bounds, and complexity, and infrared safety from ZX diagrams, a categorical proof of soft QED as open quantum system.
That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.